US Physics Olympiad, year 2012, USAPHO, Semifinal exam. This exam consists from 6 problems. First day there are 4 problems, which is part A, and the next day there are 2 problems, which is part B. For each day there are 60 minutes for all problems. Solutions for all problems you can find below this video in the description reference. Problem A1. A newly discovered subatomic particle, the S meson, has a mass m. When at rest, it lives for exactly tau equal 3 by 10 power negative 7 seconds before decaying into 2 identical particles called p mesons that each have a mass of alpha m. Part A. In a reference frame where the S meson is at rest, determine first the kinetic energy, second the momentum, and third the velocity of each p meson particle in terms of m, alpha, the speed of light c, and any numerical constants. Part B. In a reference frame where the S meson travels 9 meters between creation and decay, determine first the velocity and second kinetic energy of the S meson. Write the answer in terms of m, the speed of light c, and any numerical constants. Solution. For this reaction we can use energy conservation. It means that total rest energy for S meson turning to energies of 2 p mesons. And because we have momentum conservation, it means that kinetic energy for both p mesons are equal to each other, because momentums are in opposite directions. And we have this equation: rest energy equal to 2k plus alpha mc square, where k is kinetic energy for p meson and alpha mc square, that's rest energy for p meson. From here we can find what is kinetic energy for each p meson. That will be this expression. That's an answer for part 1. Second, the momentum. For each particle we have equation. In our case, each p meson has energy 1/2 mc square. It means that for p meson we have this equation. From this equation we can find that momentum equal this expression: mc multiplied by square root from 1/4 minus alpha square. For particle of mass m, we have momentum p equal gamma mv and energy equal gamma mc square. And we can divide momentum by energy and find what is the speed. The answer for speed, v, equal finally c multiplied by square root from 1 minus 4 alpha square. That was the answer for third part. Question B. In a frame of reference where S meson travels 9 meters, we have a distance d equal speed multiplied by time, and time equal gamma multiplied by tau, which is time in frame of reference of S meson. So it means that gamma, that's a time delay factor. And we just need to solve this equation to V. So we have this equation from this equation, and after all we have V square equal this expression. Now let's put numbers. After putting numbers, we have V square equal 1/2 C square. It means that V equals C over square root from 2. And finally, kinetic energy for S meson equal gamma minus 1 m c square, which is square root from 2 minus 1 mc square. That's the answer for final question. Problem A2. Solution for this problem you can find below this video in the reference of the description. An ideal but not necessarily perfect monatomic gas undergoes the following cycle. The gas starts at pressure P0, volume V0 and temperature T0. The gas is heated at a constant volume to a pressure alpha P0 where alpha greater than 1. The gas is then allowed to expand adiabatically. No heat is transferred to or from the gas to pressure P0. The gas is cooled at a constant pressure back to the original state. The adiabatic constant gamma is defined in terms of the specific heat at a constant pressure Cp and the specific heat at a constant volume Cv by the ratio gamma equal Cp over Cv. Questions. A. Determine the efficiency of this cycle in terms of alpha and the adiabatic constant gamma. As a reminder, efficiency is defined as a ratio of work out divided by heat in. B. A lab worker makes measurements of the temperature and the pressure of the gas during the adiabatic process. The results in terms of T0 and P0 are in this table. Plot an appropriate graph from this data that can be used to determine the adiabatic constant. C. What is gamma for this gas? Solution. As we can see on this PV diagram, we have isochoric process from point 0 to point 1. After that we have adiabatic expansion from point 1 to point 2. And after that we have isobaric compression from point 2 to point 0. Now let's count all these parameters PVT for each point. In point 0 we have parameters are P0, V0, T0. In point 1 we have the same volume V0, but due to proportionality of pressure and temperature for isochoric process, we have pressure is alpha P0 and temperature is alpha T0. During isochoric process from 0 to 1, that was heat Q01 added to this gas, which is number of moles multiplied by heat capacitance Cv multiplied by temperature difference. So that will be NCV multiplied by alpha minus 1 T0. After that, using formula for adiabatic expansion, connecting pressure and the volume, we can find what is volume in point 2 using this formula. We can use known numbers alpha P0 for P1 and find what is V2. So we have V2 equal alpha power 1 over gamma multiplied by V0. Next step, due to proportionality of temperature and volume during isobaric process from 2 to 0, we have temperature T2 equal alpha power 1 over gamma T0. And now we can count what is the heat transfers during process 2 to 0. That will be number of moles multiplied by heat capacitance for constant pressure and multiplied by temperature difference T0 minus T2. And that's equal this expression. Now we can count what is work done by gas. That's Q01 plus Q20, which is equal this expression. And last step is to find what is efficiency. Efficiency is work done by gas, which is W divided by Q in, which is Q01. So finally efficiency equal work done by gas over Q01, which is 1 minus this expression, where gamma is a relation between Cp and Cv. Question B. A lab worker makes measurements of the temperature and the pressure of the gas during the adiabatic process. The results in terms of T0 and P0 are in this table. Plot an appropriate graph from this data that can be used to determine the adiabatic constant. For adiabatic process, we have this expression is constant. It means that we have this expression for adiabatic process. Now let's take a logarithm from both parts. Now we have this dependency that this logarithm equal some kind of coefficient which we can call slope multiplied by this logarithm. And because we have this data, we already have this relation as a table, and we can plot this graph and count what is the slope of this graph. From this graph we can find that this slope equal approximately 3.5, and it means that gamma equal 1.4, and this gamma related to diatomic gas. That was actually an answer for question C. US Physics Olympiad, year 2012, USAPHO, Semifinal exam. Problem A3. Solution for this problem you can find in the reference of the description below this video. Two infinitely long concentric hollow cylinders have radii A and 4A. Both cylinders are insulators. The inner cylinder has a uniformly distributed charge per length of plus lambda. The outer cylinder has a uniformly distributed charge per length of negative lambda. An infinitely long dielectric cylinder with a permittivity epsilon equal K epsilon 0, where K is the dielectric constant, has inner radius 2A and outer radius 3A. Is also concentric with the insulating cylinders. The dielectric cylinder is rotating about its axis with an angular velocity omega much less than c over a, where c is the speed of light. Assume that the permeability of the dielectric cylinder and the space between the cylinders is that of free space, μ0. Question A. Determine the electric field for all regions. Question B. Determine the magnetic field for all regions. Solution. Question A. For this question, we can use a regular problem for infinite wire with a uniformly distributed linear charge with a linear charge density lambda. We can construct a Gaussian cylinder with the length L and concentric with this construction with the radius R. So for this cylinder we can use a Gaussian formula that integral due to surface of side of this cylinder equal Q in over epsilon 0, where Q in is charge inside of this cylinder. And because electric field is radial, we have this Gauss formula equivalent to this formula, that electric field multiplied by side area of this cylinder equal to linear charge density inside of this cylinder multiplied by length of this cylinder and divided by epsilon 0. From here we can find what is electric field. So electric field equal lambda inside of this cylinder and divided by 2 pi r epsilon 0 and multiplied by unit vector r radial to this construction. And now we can write solution for applied electric field in this form, because for radius less than a linear charge equals 0. For radius between a and 4a, linear charge is lambda, and for radius greater than 4a, again linear charge cancelled equals 0. But because we have dielectric in field between 2a and 3a, we have electric field there reduced by factor k. And finally we can write this solution. So finally electric field equal this expression in 5 different regions. That's the solution for question A. Now let's analyze this result from point of how could we get this result, because we have real electric field equal this one. It means that the electric made a charge redistribution. It was induced charge on inner radius and induced charge in outer radius of this dielectric surface. And to get this kind of electric field, we need to put linear charge density on inside surface of this dielectric. That will be negative lambda I, where lambda I equal 1 minus 1 over k lambda. And on the outside surface of this dielectric we have linear charge density lambda I. This is how we can get this result for electric field. And this we need to solve question B, because now the dielectric will rotate and this linear charge will produce electric current, which can produce a magnetic field. Let's do question B. So for question B, we just found that the electric produced linear electric charge density on outside surface radius 3a lambda I, which is equal to this one, and on inside surface with radius 2a we have a linear charge density negative lambda a. when we rotate this dielectric with the angular speed omega, we will get kind of a solenoid. Due to symmetry, we can expect that magnetic field outside of this dielectric will be 0, and inside, in radius less than 2r, that will be 0 again, and that will go parallel to this cylinder inside of the electric, means between radii 2a and 3a, and we can construct Amperian loop where we have a rectangle with one side parallel to cylinder on distance r greater than 2a and less than 3a, and the other side is far away from this cylinder where magnetic field is 0. In that case we can write Ampere law, and on this loop we have this equation. This linear integral must be equal μ0 multiplied by current through this loop. It means that this integral equal PL, which is equal μ0 I in, and I in equal lambda I multiplied by omega L over 2 pi. Now we can count what is magnetic field inside the dielectric. And finally we have a magnetic field inside of this dielectric equal this expression, and outside it's equal 0. US Physics Olympiad, year 2012, USAPHO semifinal exam. Problem A4. Solution for this problem you can find in the reference of the description below this video. Two masses M separated by a distance L are given initial velocity v0 as shown in the diagram. The masses interact only through universal gravitation. Questions. A. Under what conditions will the masses eventually collide? B. Under what conditions will the masses follow circular orbits of diameter L? C. Under what conditions will the masses follow closed orbits? D. What is the minimum distance achieved between the masses along their path? Solution. First, let's write new variable big R, which equal to L over 2. That will be distance from planet to a common center of mass in initial position. In these units we can write expression for gravitational force between these two masses. That will be gm square over L square, or using R, this expression. So now we can replace this problem by rotation around center of mass as a new center of potential. In this case, potential energy of the planet rotating around this center of mass equal this expression. Now we can write expression for full energy. That will be potential energy plus kinetic energy, which is this one. Of course, to answer for the question A, we can use energy conservation and angular momentum conservation, but this is the long way. We can use a shortcut here, because there is a known fact that total energy could be expressed through the half of semi-axis of big axis of ellipses for which this planet rotates. Suppose that the planet rotates using this ellipsis, and this point is center of gravity. In furthest position, the distance from planet to this center is big R, and in the closest position is just the radius of the planet. In that case, both planets will just touch each other in the closest position. And using this geometry, we can count what is the total energy for this construction. That will be this expression, or that will be negative 1 over 4 g m square over small r, which is the radius of planet, plus big R, which is initial distance from planet to center of mass. And now we can just equalize these two energies and find the expression for velocity. This is our equation, and the square of velocity equal this expression, or if we go back to L, we have this expression. For exactly this velocity, these two planets in the closest position just will touch each other. It means that for velocities less than this expression, they will collide. That's the answer for question A. Question B. Under what conditions will the masses follow circular orbits of a diameter L? First, let's write the expression for gravitational force between these two masses. That will be g m square over L square. But from the other hand, this force which holds this planet on a circular orbit, it means that it must be equal to centripetal force mv square over radius, which is L over 2. And from here we can find what is the speed for circular orbit. That will be square root from gm over 2L. That was answer for question B. Question C. Under what conditions will the masses follow closed orbits? Solution. Closed orbits will be when total energy must be less than 0. It means that potential energy plus kinetic energy must be less than 0. If it's greater than 0, it means that on an infinite distance we have still kinetic energy. Let's write this condition. We have total energy equal potential energy plus kinetic energy, which is negative g m square over L plus 2 times kinetic energy. And this must be less than 0. From here we can find that the velocity must be less than square root from gm over L. That was the answer for question C. Question D. What is the minimum distance achieved between the masses along their path? To answer for this question, we can just use a result when we did question A. When we answer for question A, we wrote this equation. Here R was maximum distance, which is L over 2, and the small r could correspond to smaller distance. And this is smallest distance, so we can count from this equation. Finally, we can count that r, that minimum distance must be equal this expression, or in previous units there will be this one. That was the answer to question D. US Physics Olympiad, year 2012, USAPHO, Semifinal exam. Problem B1. Solution for this problem you can find below this video, in the reference of the description. The particle of mass m moves under a force similar to that of an ideal spring, except that the force repels the particle from the origin. F equal positive m alpha square x. In a simple harmonic motion, the position of the particle as a function of time can be written in form of a cosine omega t plus b sine omega t. Likewise, in the present case, we have x as a function of t for some appropriate functions f1 and f2. Question A. f1 and f2 can be chosen to have the form exponent power rt. What are the two appropriate values for r? Question B. Suppose that the particle begins at position x at point 0 equal x0 and with the velocity v at point 0 equal 0. What is x as a function of t? Question C. The second ideal particle begins at position x at 0 equals 0 with the velocity v at 0 equal v0. The second particle becomes closer and closer to the first particle as time goes on. What is v0? Solution. Newton's law gives us this differential equation for this form of force. If we use x as a form of exponent power rt, we will get this equation. After taking a second derivative from this function, we will get expression for r that will be plus or minus alpha. That's the answer for question A. Question B. So, solution for this equation has the form a multiplied by exponent power alpha t plus b exponent power negative alpha t. Now we can use data for initial value of x and v. For x in point 0 we have x0 equal a plus b, and for speed v in point 0 we take first derivative from this expression, and for point 0 we have alpha a minus alpha b equals 0. Finally, we have a equal b equal x0 over 2, and the function will look like this. X as a function of t equal x0 over 2 multiplied by exponent power alpha t plus exponent power negative alpha t. So that's the answer for question B. Question C. Second particle at the position x0 equals 0 and the velocity in point 0 equal v0. Now let's count these coefficients for this particle A and B. Now we have these two equations for coefficients A and B. It means that B equal negative A, and we put it here and find that A equal V0 over 2 alpha and B equal negative V0 over 2 alpha. And the function look like this. So for second particle we have this behavior. And now when time going to infinity, negative exponent going to 0, and because these two particles going closer to each other, we have x0 over 2 equal v0 over 2 alpha. It means that v0 equal alpha x0. That's the answer for question C. US Physics Olympiad, year 2012, USAPHO. Semifinal exam. Problem B2. Solution for this problem you can find below this video in the description reference. For this problem, assume the existence of a hypothetical particle known as a magnetic monopole. Such particle would have a magnetic charge Qm, and in analogy to an electrically charged particle would produce a radially directed magnetic field of magnitude B equal mu0 over 4 pi multiplied by Qm over r square, and be subject to a force in the absence of electric fields F equal Qm multiplied by B. The magnetic monopole of mass m and the magnetic charge Qm is constrained to move on a vertical, non-magnetic, insulating, frictionless U-shaped track. At the bottom of the track is a wire loop whose radius B is much smaller than the width of the U of the track. The section of track near the loop can thus be approximated as a long straight line. The wire that makes up the hoop has radius A much smaller than B and the resistivity ρ. The monopole is released from rest a height h above the bottom of the track. Ignore the self-inductance of the loop and assume that the monopole passes through the loop many times before coming to a rest. Question A. Suppose the monopole is a distance x from the center of the loop. What is the magnetic flux Fb through the loop? B. Suppose in addition that the monopole is traveling at a velocity v, what is the EMF E in the loop? Question C. Find the change in the speed dv of the monopole on the trip through the loop. Question D. How many times does the monopole pass through the loop before coming to a rest? Solutions. Question A. Suppose the monopole is a distance x from the center of the loop. What is the magnetic flux Fb through the loop? First, let's draw the whole picture. This is our U-shaped track, and this is a wire loop with a radius b somewhere in the middle of this track. And let's draw the picture when this monopole is distance x from the center of this loop. On the right picture we are showing this scheme for this loop. The red line is a side view for this loop, and suppose that our magnetic charge is in point O on distance x from the center of this loop. We have to count what is magnetic flux through this loop. To count this magnetic flux, we don't need to count it exactly in the plane of this loop. We can change the shape of this surface and make it round as for this sphere, and the magnetic flux will be the same as for this plane or for this segment of this sphere. And we just need to count what is the area of this segment, because magnetic field on this sphere will be the same, and we just need to multiply magnetic field from this charge by area of this segment. And there is a well-known formula for this area. This is the magnetic flux through this area S, which is yellowish segment, and we just need to count this area, and from geometry we can say that it's equal to this expression. It's 2 pi r multiplied by height of this segment, which is r minus x. And finally, when we put it to this formula and express r through x and b, so finally magnetic flux equal this expression, where x over square root x square plus b square, that's cosine theta 0. That's the answer for question A. Question B. Suppose in addition that the monopole is traveling at a velocity v, what is the EMF E in the loop? Here we can use the change of magnetic flux with a change of this monopole position, and we count how fast is this change of this flux. First of all, EMF equal negative dFB over dt. That's expression for EMF in the loop. And now we can put expression for FB using this formula. And finally for EMF we have this expression, which we can turn to this one, mu 0 qmv over 2b multiplied by sine cube theta. That's the answer for question B. Question C. Find the change in the speed delta V on the monopole on one trip through the loop. So first let's count what is current through this loop. That's equal EMF over total resistance. Resistance equal resistivity multiplied by length of this loop and divided by cross section of this loop, which is rho 2 pi b over pi a square, and finally resistance equal resistivity multiplied by 2b over a square, and current equal this expression. After that we can count what is a magnetic field created by current in this loop in the point of magnetic monopole. There will be this expression, and we can count this integral. So this integral equal to 2 pi b sine theta over r square, or total magnetic field equal mu 0 I over 2b multiplied by sine cube theta. After that we can insert expression for current I and expression for EMF E, this one. Now we can count what is the force on this magnetic monopole. It will be Qm multiplied by magnetic field, and acceleration equal force over mass. And we have acceleration equal this expression. After that we can count what is the change of velocity. Now using expression for acceleration we can find what is the total change of speed. That will be integral from negative infinity to positive infinity from acceleration multiplied by delta t. But delta t approximately equal dx over v. We can approximately make this expression. After that express dx through theta. That will be dx over dt multiplied by d theta. This dx over d theta equal negative b over sine squared theta. And finally we have this integral, and here we can insert the expression for acceleration. Now after a cancellation b and v, we have dv equal this expression, and we have to count this integral. Let's do this. Let's count what is this integral from 0 to pi of sine power 4 theta d theta. We can represent sine power 4 theta through multiple angles. That will be this one or this one. And finally, if we take integral from this part, integral from cosines will be sines, which is 0 from 0, 0 to 0, that will give 0. And the rest we have 3 over 8, which is constant, and finally this integral equal 3 pi over 8. And we can put this result to this formula. That will be our final result for delta V. That's a negative, this expression, which is the answer for question C. Question D. How many times does the monopole pass through the loop before coming to a rest? As we can see, delta V is always negative. This is due to Lenz's law, because change of magnetic flux create the EMF, which is try to reduce this change of magnetic flux, which work against the motion. And this is always dV is negative. Number of turns could be found dividing initial speed v over dv. And initial speed we can find from energy conservation. That will be square root from 2gh multiplied by this expression and divided by this expression. That's the answer for question D.